So here's my presentation for CS525 final project. This is the flowchart of the project. We use the parser to build an abstract syntax tree for Lambda. By translating to level 1 and doing type check, we make sure all names are bound with values before we reference them and the program is well typed. Then we can either interpret the program or translate it to level 2, which is an intermediate representation that can be easily compiled to C. The translation supports tail recursion optimization for unary function. We can rewrite unary function to use one tuple argument so that they can benefit from it too. When compiling level 2 to C, extra code for garbage collection is generated, but the support for GC mainly comes from the runtime. As the parser is provided, let me start from translator 01. The translator resolves all binding issues and does some basic work for type checking. For example, when meeting a literal one, it labels int type to it. Let's see some code. A program of level 0 consists of a global declaration list and a level 0 term. For each item in the list, we create a new level 1 variable, then translate the corresponding level 0 term according to current environment. Finally, we update this environment and pass it to the next item. After processing all items, we get a level 1 declaration list and an environment. We use the environment to process the term. The logic is straightforward, but there are points we should pay attention to. When meeting a variable, it should be found in current environment. Otherwise, an undefined reference happens. Recursive function's name should be added to the environment. Let declarations are treated similarly to global declarations. Tuple needs special care. There's a list to pair conversion involved, and the one element tuple isn't actually a tuple. We have to add a nil if the else term of a condition is missing. Let's see the result for fact.lam. Here some types are blank. The functionality of type checker is to find type error and to deduce the blank types. We call type 1 unify to make sure two types are the same and no illegal occurrence. To handle x equals to x case, we do nothing when we unify two same blank types. To handle x equals to tx case, we check whether x occurs in the given type by calling occurs check, and if so, type 1 unify refuses to fill the blank and returns false. From the previous output, we can see all blanks are filled. Our interpreter is closure-based. Whenever it meets a variable, it stores the value and fetches it when needed. Here are the parts I implement. When comparing a variable with another variable in the dynamic environment, their stamp value is used instead of variable name. the stamp is actually an automatically increased integer. The global declaration list and the term representing main function body are treated as a let term in level 1, which simplifies the logic. An escape function is implemented, so if a string contains line feed, we get prettier output. Let's talk about the design of level 2. Before the project announcement released, I implemented a draft compiler that directly compiled level 1 to C, but after that I decided to refactor the code to use level 2 for the following reasons. Previously, string concatenation is everywhere, and the code is poorly maintainable. For example, later when I add GC support, I wrap all assignment statement to a function call. I don't want to find all these and then replace them with this, which would be error prone. The structure of the C code to be generated is embedded in the ATS function as strings and variables, which is unclear and also decreases maintainability. Refactoring it just the day after writing it was painful. As a result, a new level close enough to C program must be defined, and the process of emitting C code should be loosely coupled with translation. But one side effect of doing this is that I can easily add indentation support. Here are formulas of data structures. A program is a function list plus a block for main. A function has a name, a parameter, a boolean indicating whether it's recursive, and a block. A block is a declaration list and an instruction list. They are separated to support GC. There are only 3 kinds of instructions: assignment, condition, and loop. There are 13 kinds of lambda values. They are for literal operation and reference. We also have data structures for environment. Before we diving into the core function of translator 1.2, let's take a look at some important auxiliary functions. Whenever we need a temporary variable, we call newTemp to generate one. FESet computes the free variable set of a term in level 1. We need this information to construct a closure. getVar is called whenever we reference a variable. The variable may be locally declared in the environment or a recursive reference to the current function. The core function is trans1 to term1. It takes 8 arguments and returns the updated version of the first 3, reflecting current state. FunDef is the known function list till now. BlockDCL is the variable declaration list of the current block. Ins is the instruction list of current block. Whenever we meet a new function definition, we update FunDef. Whenever we meet a new variable definition or need a temporary variable, we update BlockDCL. Whenever a new operation is performed, we update ins. When updating them, we prepend instead of append for better time complexity. Holder is the name of variable to hold the value of current term. The function is called by trans12 TPGM, which takes a level 1 program and returns a level 2 program. For simplicity, we wrap global declarations as a let term. Some details of this function. For a variable, we call getVar. Then prepend an assignment to the instruction list. For a lambda function, we first generate a unique name, then compute the free variable set of the function. Next, we call trans12 term1 to translate the function body. Now that we get the function body representation, we can prepend the function to function definition list. We assign a closure with environment to the value holder variable, where environment consists of all variables in the free variable set we computed. We handle a recursive function in a similar way to lambda function, but we need to get the parameter and function body first. Another difference is that we mark the function as recursive when prepending to fundef. For a condition term, we evaluate the function, then we evaluate the condition, then call trans12 term1 twice to get the if block and else block. Here. Dealing with function application is important, as it's where tail recursion optimization takes place. To be a tail recursive call, 3 conditions must be satisfied. First, the function to be called is a variable. That is not a term that will finally be evaluated to a function. The second is the variable is exactly current function. That is, we don't optimize mutual recursive or n-array recursive function calls. And finally, the result of the call is the value to be returned. That is, the holder of the result is variable ret. If it is a tail recursive call, we mark it as optimizable and modify the parameter. Otherwise, we have to evaluate the function to be called and make the call. For emitting the C code, this is a relatively easy part. Every data structure directly mapped to some strings. As mentioned before, lists should be printed recursively. An integer indicating the level of block is maintained to support indentation. Although the generated C code is not for reading purpose, it's always convenient to analyze and debug formatted code. The main function of lambda returns a lamvol. To show this value, a lamvol print is added to the main function of C. Let's compile for f91.lam. As we can see, there are 2 normal function calls in main and else block of F0. which is the inner recursive call to F91, but the outer call is a tail call so that it sets loop to 1 and updates the parameter x1. Our tail recursion optimization works. Let's compile it with debug macro and run. The last two lines show that in the end we collect all garbage and get the correct result. When talking about GC, let's run coin change with or without GC in background. We modify 100 to 1000. Okay, let's see the activity monitor. Inspired by C++, reference count is used to implement GC because the purpose of GC is to save memory and the value is immutable in Lambda, so we don't do deep copy. It's much simpler than mark and sweep used in JVM, and it has better performance than mark and sweep. No circular reference happens, which is the main drawback of reference count, so we can safely use it. The approaches to collect garbage by reference count is ref assignment. We increase the ref count of the value. Clean at the end of block. We decrease the ref count. If it reaches 0, we free it. Tuple and closure are freed in recursive manner. Every environment has a head node that doesn't reference any value. Instead, its key field stores the reference count of the environment in recursive function. If the same environment is referenced, we increase the count. When we call a function, we increase the argument's ref count. When we leave a function, we decrease the parameter's ref count. The return value's ref count also needs decreasing, but it shouldn't be recycled, even if ref count reaches 0. When doing tail recursion optimization, we modify the parameter pointer. That's the only case that rebinding happens. So before we assign a new value to the parameter, we should decrease the ref count of the original value. Okay, the two programs are done. By watching activity monitor, we notice that without GC, the program's memory load is steadily increasing, reaching 20 gigabytes in the end. But with GC, the memory load seemed fixed at less than 4 megabytes. GC did bring some overhead. We can see the time here. But the benefit is we reduce the memory needed by more than 99%. What I learned from the project is making a compiler is not an easy task, while building an AST and interpreting it is highly formalized. Generating code for the AST is not. But we never understand it before actually implement it. Efficiency is of vital importance for both the compiling process and the generated code. Thank you.